This is example 5-8, water pumped uphill. So you can see we have a lower reservoir at A. We pull water out of the reservoir, it goes through a pump. That pump pushes it all the way up to a higher reservoir at B. And we're given the flow rate inside of these pipes. We're given the diameters of the two different, like the pipe and I guess you can call it a hose. And now we're asked how much power we need to supply to the pump to get this moving, and we're told that the friction head losses within the pipe systems are based on the flow in the larger of the two pipes. And that's quite common because of course the faster the water is moving, the more friction we're going to have, and the more that means we get more of losses. All right, so what are we going to do? Well, of course we're going to use our energy equation, so we can write that in here. We'd have P in divided by gamma plus V in squared over 2G plus Z in plus H pump, and all that is equal to the other end, which is P out over gamma plus V out squared over 2G plus Z out, it almost looks like a plus, plus H turbine plus the head losses. Right, that's what we get. And now we have to decide where is our in, where is our out. Well, in our case, the water is going from the reservoir up to here. So we will say our starting point is going to be somewhere on the surface here of A, and our end point is going to be where the water spills out on the other side. So this will be our in, and this will be our out. So let's go ahead and look through those values. We'll start, well, usually the easiest one is the datum, and so we'll set the datum at the surface of this reservoir. So datum at surface, not two F's, but an R in there somewhere. Surface of lower reservoir. That means that our ZA, our Z in, is equal to 0 because it is at the surface of the reservoir. And ZB is the out, or we are given that we get a height there of Z of 30 meters. So ZB equal to 30 meters. There we go. All right, so we'll assume that this height difference between where the water comes out and the surface is real small. So we'll just say it's the same. So that will be the surface. Now maybe one other thing to point out, right? We're choosing it at the surface of this, not down at where the pipe begins, because we wouldn't have, we wouldn't know what the pressure is, and we don't even know what the depth of that hose is and all those kind of things. That's why we have to choose it at the surface. So that will be our two elevations, Z in and Z out, ZA and ZB. So then we can also look at the pressures. Now point A is at the surface of the reservoir, and point B is a free outfall, so both of those are going to be 0. So we can say point A at surface and point B free outflow, which means that both of them are going to be 0. Right, so we know PA equal to PB equal to 0. All right, that's all good. How about the velocities? Well, if we think about the lower one here as a big reservoir, then we can say point A at surface of reservoir All right, and remember that if we have our location at the top of the reservoir, right, then we are going to assume that the change in water level is going to be very slow compared to how fast it's moving through our system. So we can say VA equal to 0. Now how about VB? That's of course not going to be 0 because we're going to have things flowing out. But we're given what the flow or the volumetric flow rate is, and we're given the diameter. So we can just use that, right? So we can say velocity at point B, velocity at B. There we can say, well, we know that Q is just going to be the velocity at B times the diameter at B, times the area at B. I'm sorry, we'll get to the diameter in a second. All right, so that means my VB is just going to be Q over AB. That means Q over 4 over pi dB squared, or 4 times Q. The wrong way around. Oh. Let's go back here. For some reason I keep on writing it the other way around. I think it's pi over 4, not 4 over pi. Pi over 4 times dB squared. Then it works. Then we get 4 times Q divided by pi times dB squared. Can put those numbers in, and we get 4 times 0.035 cubic meters per second divided by pi times, what was our diameter of the larger pipe, 50 millimeters, 0.05 meters cubed, not cubed, squared. Where are we going here? All right, and that gives me 17.82535 meters per second. So that work with units. We get square meters and cubic meters. Yes, we get 8 meters per second. All right, what else do we need to know in our equation? So let's see. We have found the pressures, we found the velocities and the elevations. H pump we're looking for. We have no turbine, and we're given what the HL is. So let's say H turbine. So no turbine. Which means H turb equal to 0. Now we're looking for what the pump is, yes, so that we don't have to specify that. But we'll have, the next thing is that our frictional losses depends on VB. Right, again, faster the water is flowing, the more friction, so the more loss. And we're given an equation for it that is just 3 times VB squared over 2G. Looks exactly like our velocity head. And so we can take all that and stick that into our energy equation that we have up here. We'll have a whole bunch of zeros. Well, we start out with our first pressure, our inlet pressure is 0, our inlet velocity is 0, and then our elevation is 0 as well. Then we go to the term that we're looking for, H pump. And then we said the pressure at the outlet is 0. We figured out what VB is, VB squared over 2G. We know what ZB is. There's no turbines. And then we have HL. Now, the cool thing about HL, of course, is that it's given as in terms of VB. So we can say if we solve this for H pump, well, we don't really have to solve it. We just have to write it without all the zeros, right? So we'd have VB squared over 2G plus ZB. Now, HL is given to us as 3VB squared over 2G. Means we can combine those together, right? So we'd have 4VB squared over 2G. 4 divided by 2 is 2. So we'd have 2VB squared over G, and then still plus our ZB. And then we can plug that in. That gives us 2 times VB we calculated earlier somewhere. There. 17.825 and so on and so on. 17.82535 meters per second squared. G is 9.81 meters per second squared. And then plus our ZB, which was 30 meters. And that gives me 94.7794 meters. Let's see if that works out. We have meter squared, second squared meters. Yes, and the meters here, of course. That all works out. So now I have the head from the pump, and I can convert that to what the power would be by saying power of the pump is equal to Q times gamma times H pump. That would be 0.035 cubic meters per second times 9,810 Newton per cubic meters times what we just calculated, 94.7794 meters. Let's see if that works out unit-wise. Well, let's write the number first. So I get a number of 32,542.5. Now let's see. We have newtons. The cubic meters cancel out, so we have Newton meters per second, which is good because that's the we want to get. That'll be watts. And then we say we end at 10,000, so we can say this will be 32.5 kilowatts. That would be our result. All right, so in other words, if we had the following setup here, then the pump would have to deliver 32.5 kilowatts and able to lift the water from the one reservoir to the other, and to have it flow out with that specific volumetric rate.